Thank you very much for the invite to be at this prestigious conference, and thank you all for being here on a Sunday morning. That's quite commendable, especially for all the young people. So since it's early, I'm going to start by playing a video, and I'm going to let you read the subtitles for a while. Who's seen this video before? Ferial? So that was basically the first time someone jumped backward. Nowadays, everyone does that. That's how we do the high jump. In previous years, people would do all these sort of crazy trial and error attempts at getting the most height. Now, the reason why I like to show this video in talking about imitation is it clearly shows that since there are these sort of big steps, these huge creative steps that come as a result of exploration, and in this case, they also come as a result of abstraction. So the story is that this guy, Dick Fosbury, was a student of physics, and he actually went and calculated the center of mass of a human body, etc., and knew that if he curved his body backward, as long as the center of mass went over the bar, he could get through. So this is using abstraction, symbolic reasoning, to actually do a huge step. But what's important is that once Dick Fosbury was able to do this, everyone else did the same. The other thing Dick Fosbury did, if you keep watching this video, is he actually arrived at the Olympic Games the night before, and he slept in his van. It's like nowadays it would be crazy that an athlete would arrive at the Olympic Games and sleep in a van, and then no. Nowadays they arrive with a huge team of massagists and the people who know exactly what drugs they should take, which ones they shouldn't take, etc., etc. And it's a big production to get an athlete to perform in the Olympics. So people copied some traits of about some behaviors, but not all behaviors. And that ability of us of identifying successful behaviors and being able to quickly replicate those is a huge step, I think, in intelligence and in evolving intelligence. If no one imitated, then that behavior could have died with Dick Fosbury, or it would have taken a long time for that behavior to replicate across a small population. But no, when there is a successful behavior, it gets replicated very quickly. This video also shows that it's not all about imitation. There was that created, there was a step of abstraction, there were steps of exploration or of creation. My personal feeling for this, a hypothesis, is that these processes have co-evolved. And imitation drives abstraction, and abstraction has driven imitation. Now, what I just said is controversial. That previous video is also very controversial because some people use that video to prove that imitation is irrelevant. And some people use that video, as I have done, to prove that imitation is a very important thing. Imitation is very hard to define. There's been definitions since the 1800s and so on. No one agrees on them. And because it's hard to define, if you start looking into the literature, especially the literature of this community, which is quite eclectic, you will find hundreds of definitions. And if you go into the literature on animal behavior, whether, especially trying to see what animals have and don't have in terms of intelligence, then things get really heated and debated. I thought in my talk I was going to go into that, but I thought that for this audience that would be a career suicide. So I decided to instead focus on technical aspects of imitation engineering. But one thing that is worth pointing out is that quite often what people refer to as imitation in nature, by birds, monkeys, and so on, I actually do see as reinforcement learning. And not only do I see it as reinforcement learning, I know how to implement a reinforcement learning agent that is capable of those behaviors, which makes me feel that this hypothesis that the animals are really understanding what another animal is doing and copying that behavior is wrong. Like, for example, if a bird sees another bird, if it's going to a bottle of milk and making a hole and drinking milk, then maybe what that bird really is seeing is a red pixel. When red pixel gets close to white pixel, there is reward. And it knows this because the closer it is, the bigger red pixel is, the more chance it has of getting reward, the more sort of it gets the milk. And just by pure reinforcement, it can learn to imitate another bird to go and get milk from a bottle in front of a house. So for this, and for a lot of other behavior of like monkeys imitating other monkeys, say, by having different calls for eagles and so on, these are behaviors that can be learned purely by reinforcement learning, so there's no need for imitation. I think when I talk, you know what, I will talk about imitation without defining imitation, and though I will just use a colloquial way of thinking about imitation. But I'll try to come back to this question of definition at the end. I'm going to focus on what has worked for us doing imitation and machine learning. And my hope is that some of the insights that we've gained will be prove as some inspiration for you as you're formulating hypotheses, or help you falsify some of your beliefs. In machine learning, we're interested in several aspects of imitation, and I've listed the 6 that interest me here. The first one is one-shot rapid imitation, and that'll be a good part of the talk. And in short, is if you see someone doing something, how do you quickly, just by watching one instance of the person doing that behavior, how do you copy that behavior? So very rapid thing. If I see someone, I don't need to see birds one after the other going for the milk and looking happy. I just need to see one, and then quickly I know that I can do that. I can sort of go to the milk and drink my milk. Third-person imitation is about doing the sort of remap from one body to another body. So it's like me imitating a bird with completely different bodies, but we can both go and drink a bottle of milk. In imitation, I consider 2 different kinds. There's a high fidelity, which is when I want to follow a motion precisely, or act in some objects in the same precise way, or grab the same objects, do precisely the same behavior. So this would be, for example, if I'm trying to learn to play flamenco guitar and I want to imitate precisely what one of the great masters does, then I don't want to just, I don't have a reward other than just trying to be as close as possible to the person I'm imitating. And this, you could see, could be useful for someone, for example, trying to teach a machine how to do something, if it's, say, surgery or something, and where there might not be a goal. What you want is for the machine to follow the procedure precisely. Another goal in contrast to this, that there is the intentional imitation. So an intentional is when there is a goal and there's an action plan. So you want to achieve something, you don't necessarily need to achieve it in the same manner. So I might want to reach to my phone, and maybe if I want to do it with my right hand, I might have to do something else than someone else who wasn't holding one of these. Finally, there are two topics I'm not going to cover here in the talk in the sense of presenting results, but I want to sort of open these up to this community, especially the young folks in the audience and so on, because these are very important topics. How do you imitate long behaviors? Like if you go to someone's house in the afternoon on Sunday and they cook this huge meal for you, you'd like to replicate that the next Sunday for some other friend. Imitating a whole afternoon of cooking is beyond any AI agent that we have at present. In fact, imitating beyond thousands of steps is beyond any reinforcement learning or imitation algorithm we have at present. And finally, there's this question of selective imitation that I just pointed out before. That we select which behaviors to imitate, we select who to imitate, and so we can have different ways of doing the same thing, for example. So this, I think, is very important to attain abstraction. I'm going to start with one-shot imitation, and one work that I will just go briefly over it, I'm not going to make much justice to it, is this MAML meta-learning algorithm. Just to get a sense of this audience, how many of you have worked before with or know of meta-learning, have read a paper about meta-learning, a blog? MAML? Okay, a few of you. So meta-learning is, I think, a very interesting framework, and like if you like Elizabeth Spelke's talk and so on, I think you should all be learning about meta-learning, those of you who didn't put your hands up. Matt Botvinnik, a cognitive scientist, neuroscientist, one of my colleagues at DeepMind, has actually written some wonderful papers geared at the neuroscience literature, so I would recommend those. The idea in MAML is we encounter, and this kind of it will illustrate both one-shot and third-person imitation. So in this setup, we considered that there's two types of data. You have robot data, which consists of what the robot observes, which is sort of represented in this case by these images here. This is what the robot is seeing. And you also have data corresponding to what a human observes. And then the intention here is that the human is going to say move an object from left to right, and then you want the robot to also move from left to right. The robot, of course, has a very different type of arm than the human has, and what the robot sees is very different to what the human sees. For the robot, we have some other important piece of information. We know which actions, which motor commands are given to the robot. Whereas for the human, we only observe the images. If you have the observations and the actions, then imitation is simply here about learning a map, here with a neural, these days always with a neural network, that will take images as input and produces actions as output. That mapping from observations to actions we call a policy, or policy network. Training a classifier that sort of chooses actions or regresses into actions is something that's somewhat trivial. If you have a big data set, doing so is something that we can do now routinely. The software tools are out there so that anyone, even without experience in programming, can very quickly build one of these. The other problem is more challenging. We don't have actions for the human demos. All we have is the observations. So how do we produce the actions? How do we learn a policy that will map it? The answer of MAML is to use two nested losses, or if you want to think about it, a hierarchical losses. At the low level, you unoptimize a loss such that by optimizing that loss with respect to some policy parameters, you will map observations of a human to actions. At the high level, and this, I should say, this policy, this loss function will be parameterized by parameters of the high-level loss. The high-level loss tries to map the observations of robot to actions of the robot. By learning by minimizing the high-level loss, you discover a loss such that the low level can also map from observations to actions. Now, this might sound difficult to think about in the context with neural networks and so on, but this is the same as what we used to always do in a hierarchical base. For those of you who looked at hierarchical base before, at the low level, we have, say, a likelihood. That likelihood has hyperparameters. So in other words, the likelihood loss is unknown, subject because you don't know the hyperparameters. But the hyperparameters can be learned up with empirical base. So once you know the hyperparameters, the loss by optimizing some loss above, the low-level loss becomes defined. And so now, with MAML, you learn a loss such that when you take gradient descent steps on that loss, you can actually infer a loss from the bottom. And so now when the robot is shown a video of a human, the robot can imitate that quickly. A challenge with MAML, though, is that it tends to work only for very short videos. In fact, the demos that presented with this work tend to be things like the robot is already holding the object, and it has to drop it somewhere. So it just moves it for a few steps and drops it. It continues to be a line of research how to make MAML scale to long sequences. Perhaps easier to understand way of doing one-shot imitation is via generative models. So here, as this thing shows on the left, you see this video here of a humanoid. This is in a controlled environment, so this humanoid has fields, contact forces, and so on, has weights, etc. And then on the right, there's a control policy whose dynamics you need to estimate, like 27, there's 27 possible torques that you apply to this humanoid. And you need to learn a policy that will produce those forces and torques such that the guy on the right imitates the guy on the left. And a similar work does this with robots, sort of stacking objects and so on. Now, the way this is done is you take a video, you map that video through some neural network until it produces a vector, an embedding vector. At training time, you also take a step in the video, and you will do this for many states, observations, and actions. And in order to learn a policy, you use the same axis, but you use the actions. And this is another way of a way of doing this behavior cloning, of learning a classifier that goes from the video, which is presented in two places, to the actions. The reason why we're going to do it with this embedding, the reason why we train it like this, is we train it through a huge number of behaviors, okay, thousands of behaviors. And the idea is that you will eventually learn a vector which encodes the behavior, what the video is about. So this vector is think of it as a continuous description of what this behavior was about. Then given a new observation of the environment and the behavior that you want to perform, this other neural network will choose a policy. Will choose, an action. And you can also learn a model for these simple simulated environments that predicts the next image. So the idea is you feed in the video. From the video, you get an embedding that says what this guy is doing, which behavior is being performed. And this vector is enough to decide what this is. The nice thing about having an embedding is not discrete. You could have an infinite number of possible behaviors. And once you know what the behavior is, you can now, given a new observation, choose the action. If you train this with thousands or preferably millions of behaviors, different walks and so on, what you eventually learn is a way of generalizing to any behavior, such that at test time, given a new behavior that you've never seen before, given this video, you quickly get the embedding, and then you're able to start at some initial stage, choose an action, that will transition somewhere else, you observe the world, you choose an action, and so on. So you end up being able to imitate just by following your policy, which is conditioned on what behavior it is that you should manifest. So this is quite powerful, this idea of an embedding, because an embedding can describe a whole entire behavior. here's an example how powerful these things are. So back in 2016, I worked with someone who was my intern then, Scott Reed. We created a neural network where there would be a neural network core. So this is some sort of recurrent neural network. And then the neural network would have, as inputs, whatever the neural network sees, in this case, some digits that come in as the thing that it observes, so some symbolic input. And it observes as well a vector. This vector decides what the program is that this network should execute. And it will be things like sorting, rotate images, very varied things. And you can have many of these programs in this library. The idea is this interpreter should learn to act as universal interpreter, such that it takes a program, it takes an input, it can call another program, and keep going like so in the execution of a long program. Scott also came up with the idea of adding a stack, such that you could learn sort of recursive programs. These embeddings will also be learned. In the previous slide, the embeddings are predicted given this video. But an alternative is to try to learn this embedding by backpropagation. And that's what we're going to do now. In fact, when Scott does this, here are some of the tasks that he does. And this is exactly the same neural network. So it's the same, the neural network was trained on several tasks and is able to solve all these tasks. Moreover, the neural network is, because it can be trained recursively, so researchers at Berkeley, Don Song and some of her collaborators actually showed that you can actually verify the network in the sense that if a network can sort integers of, say, can sort integers of sequences of length 20, then because it's done recursively, you can actually prove that such a network would be able to sort sequences of arbitrary length. So you can verify the neural network in this case, because you verify the inductive hypothesis and the base case. So you can get universality out of these models, and to a large extent, interpretability. It's the kind of universality that I'm not happy about, though, because it requires that you enumerate basically all situations, and it's not capable of understanding something like, no object travels faster than the speed of light. That kind of generalization is beyond any neural network at present. But one thing this thing can do is, once you've learned a library of these embeddings, suppose you want to run a new program, and that new program is, let's find the maximum element of a list of integers, then what this approach can do is it can learn to call the sorting algorithm, which is already in its library, and then it can learn a new program, in this case, take the rightmost element, so sort and take the rightmost element, and that's a way of getting the maximum. And then so Scott showed that this is possible. And we think of this as meta-learning because you've learned this core interpreter. And then as you move on, as you continue, you just keep adding more vector embeddings. You keep learning more programs. That was trained in a supervised way. And there we actually did a big cheat, which is we provided the hierarchy as supervision. So we knew which programs to call. We knew the execution trace. When you know the hierarchy, when you can cut the behavior into segments of behavior and establish a hierarchy, it's actually quite easy to learn such powerful machines. The challenge is how do we learn the hierarchy as well as the programs, all from scratch. That continues being a challenge. We've recently used reinforcement learning algorithm AlphaZero to train the model, and we were able to, together with an African company called InstaDeep, who were able to show that you can train some small models using AlphaZero, mainly thanks to the ability of AlphaZero to do these imagination steps. So for example, here it's trying to solve Hanoi towers, a recursive, difficult task for neural networks because it's recursive. it can sort of, in a particular situation, it can plan ahead to choose and backtrack to choose the action. So at each step, instead of just executing a neural network policy, you actually stop, you think for a little bit, loosely speaking, and then you act in the environment. And this is actually very powerful. So I think one of the lessons I would say that we have from reinforcement learning is that if it's possible to do this kind of thing, this turns out to be quite effective. Coming back to supervised learning, or behavior cloning, as we refer to it in imitation, one, I think, example of the powerful value of this idea of just having a network that consists of two things, a fixed core and an embedding that adapts according to the task. And for the imitating behaviors, the task was like, the embedding was behaviors, that's the task. For programs, the embedding is programs, so the task is programs. And what we're going to do now is imitate people's voice styles. And so the embedding is corresponds to voice style. So a person is a task. I think task is a very hard to define word. And people often define intelligence as an intelligent agent as one that can solve many tasks. And that is a useless definition because it doesn't define tasks. So I tend to be very, just like I'm loose about imitation, I'm going to be very loose about tasks. Tasks can be people, so as you go from one person to another one. A task will be, this community thinks a lot about tasks, so probably what I'm telling you is sort of trivial. But in machine learning, often tasks things, you go and build an environment and so on, and then you want the agent to do a specific thing, and you think of that as a task. I'm going to be a bit more loose with this. So it could be shifting from a person to another person, programs I see as tasks, and so on. So here the goal is to go from a sequence of words to speech. And the way we're going to do this is we're going to use some big neural network. With, the particular model we use is a network called WaveNet. And this sort of is very useful in going from text to speech, because one of the things we've been able to do, for example, is to go for people whose voice had been recorded previously and who have suffered from diseases of like AMD, ALS, we're able to recreate their voice so that when they use speech synthesizers, they're able, or by doing eye tracking and so on, other devices, we're actually able to empower them to actually speak again with their voices. And I've witnessed this with my team. This can be very inspirational. It's like when you see the patient there and the families there and they all start crying because they can hear the person again using their voice, it's something that is it's quite profound. It has a huge societal impact. So even though we've only helped a few people, it's been worth it. So how do we do this? Typically, this involves several steps. The training step, again, instead of thinking of, like in the old days, what we would do is take a data set of, say, 4 hours and train one big model for one particular speaker. And then if we wanted another speaker, we would retrain that model. The philosophy here will be, let's basically use the same model, but let's present the data in a different way. Let's take thousands of speakers and only give each speaker 4 minutes. And the idea is we're going to train a model that consists of many tasks with few data as opposed to few tasks with a lot of data. And again, the model is going to consist, we train them by maximum likelihood. We're going to go from a wave to text. But for each person, we'll also have information of task ID. We know which, in the training set, we know which individual, that there's unique individuals for the voice. And so we're going to have these embeddings once again. And these embeddings will be person-specific. Whereas there's going to be a core network that's going to be independent across all speakers. So this is the shared knowledge, and this is the knowledge that changes according to the individual. And the intuition here is if you try to learn a neural network that can map the voice of everyone here, that's going to have to be a massive network. A single network will eventually be able to do this, but you need a lot of resources to train such a network. Whereas if you break the network into two components, then the big network only needs to learn to model the process of going from text to speech, some generic process, and then the embedding vector, that is what is sort of tuned to each individual. So that's what gives the model flexibility. For people who've done machine learning before, think of mixtures of Gaussians. Conditional on, if you know, or like k-means or something, if you know which cluster you belong to, then learning the mean and covariance are trivial problems, they're convex problems. But if you don't know which cluster you belong to, then you have an NP-hard problem. So by conditioning on task-specific vectors or latent variables, it becomes easy to solve this other task. It becomes possible to train this. At adaptation time, so we train this with lots of speakers. Then for a new speaker, we get a bit of 4 minutes of sound and 4 minutes of corresponding text, which we can get with a speech recognizer these days. And then we adapt this embedding vector for that speaker. And once you do that, now you can feed in text and it will produce the sample wave. So I read a, which story was, can't remember if, was it? Anyway, I read some fairy tale, I forgot what the fairy tale was. And this is what the model, how the model copied my voice.
The days of meta learning are beginning.
That's after 4 minutes of grabbing my voice. One thing that we've been doing more recently, led by Yutian Chen at DeepMind, and actually I hadn't realized, but Ferial over there, she was one of the developers of this, is in these previous works, we define, there is a designer that chooses what models get to be shared and what part of the model is shared among all tasks and what part is task dependent. And so we wanted to learn something a bit more general, where you start with several modules, in this case, say 3 modules. And then for each module, we want to learn whether it should be task dependent or task independent. So what we meant to learn is a set of network parameters, the set phi1, phi2, and phi3. We learned length scales. And so essentially, when these are Gaussian, so when the variance goes to 0, theta has to be like phi. So in that case, those modules don't adapt when you go to another task. So basically, we learn across many tasks which are modules that can be reused. And then we leave some modules, and some modules will be able to adapt. So you learn what should be adaptive and what should not be adaptive. This one just went on archive about 3 days ago. If you want to learn more about it, I suggest you talk to Ferial, who's right here, and she was actually the person who drew these pictures. Do you want to put your hand up, Ferial, so everyone sees you there? Okay, so up to now, we've basically been doing behavior cloning. And so now I'm going to switch quickly to reinforcement learning. With behavior cloning, you sort of learn to mimic behavior. You learn to copy it. But sometimes we want to bring intentionality. We actually not just want to copy it, we actually want to do better. And so in reinforcement learning, you start with an agent. This agent interacts with an environment, and the agent has some goals. You might want to do something, influence other agents, or find food, or whatever goal it has. It observes the environment, and it acts in the environment. And this process of going from observations and goals to actions, we're going to model with neural networks. And those neural networks we train with reinforcement learning. So for example, one of such networks is this one that looks at observations of the environment. It has some goal of what it wants to do with the hand in the future. These images get processed through neural networks convolutional blocks. And then it outputs 2 things, which action it should use, the policy, and it also produces something that's very useful, which is what's the expected returns of following this policy? What are the sum of rewards I will get in the future? What do I expect rewards I will get in the world if I'm to follow this policy? So these are the two quantities these networks always predict. And here's some evolution over time of these networks. In the old days, actually, this is 2018. In the old days with DQN, we had like 2-layer convolutional networks. Nowadays, we actually train like these really massive neural networks. And they have to be massive. They have to understand the visual scene. That's a non-trivial thing. But what's really remarkable is we can train these models with reinforcement learning. I never thought that would be possible a few years ago. I thought the variance of reinforcement learning was too high for that, but it is possible. So that in itself has been a remarkable achievement in engineering. So starting with reinforcement learning, I'm going to give you an example of a high-fidelity imitation. That is, when we want to do this sort of over-imitation, we want to follow precisely a trajectory. So you might observe a demo that consists, and in this case, I'm going to do this in first person. So this is a robot trying to imitate its behavior. So what typically we do with robots is we teleoperate them to do something. Because it's easy to teleoperate, well, it's actually not easy. So it's a hell of an engineering challenge. But you can teleoperate a robot to do something like move a glass like this. And then it would be very hard to teleoperate it to pour. It's actually with this bottle. But we certainly can teleoperate robots much better than what they're capable of doing autonomously. Autonomously, they actually fail abysmally whenever there is any uncertainty. They work well with car manufacturing and so on because everything there is very precise. There's no uncertainty. Everything is deterministic. Everything gets pre-programmed easily. But the moment you want them to generalize, they fail. And so we teleoperate, and because we're teleoperating, we know what observations the robot gets, and we have the actions as well. In this work, Tom, the person who did this work, was Tom Payne, was just taking the observations of what the robot did, and then the goal being achieving the next observation. Those get passed through the policy, chooses an action, it goes into the environment, and then the robot observes something else that goes as an observation into the policy. Then the demonstration gives the next goal, and so on. In reality, the way we implement this is with large-scale distributed systems. There's a database of these demos. There's processes that we call actors. So actors will go to the data, using the current policy, they execute the policy and environment in the way that is here on the left, and they're able to collect a big data set of experiences that consists of observations, actions. So if you have a simulator, a model of the world is very powerful, because even though the observations only have the input only consists of demonstrations, that is, images. By simulating, you're able to get actions. If you have some metric of reward, you get that as well. You get how well you're doing, and so on. So you're able to get a very rich data set thanks to imagination. You can imagine what rewards you will get, what actions you will have to use, and so on. We throw all this into a big database that we called experience replay. And then a learner uses some reinforcement learning loss very similar to what DQN does. In this case, it's this DPG. Deterministic policy gradients. It queries the database for data, and then it learns to imitate. And here is an example where it's doing this high-fidelity imitation. There's a demo on the left, and then the imitation will do something that's, this is simulation. The graphics look realistic, but it's actually simulation. And it's able to do this quite well. Now, if you have that database, now what you can do now is to also build an intentional agent. Because suppose you have an intelligence, an agent that actually has rewards in mind. Then that agent can act in the environment, again, through several threads or actors. And then the learner can reuse not only the data that's coming from the current task, but it can use all the previous data that you learned through over-imitation to actually achieve a task much more efficiently. So this is a powerful thing about reinforcement learning these days, especially these ones that use experience replay. Our off-policy algorithms now are beginning to work. In particular, there's something called distributional reinforcement learning. I'll repeat it, distributional reinforcement learning. It's one of the most powerful things we have at present. It allows us to actually, to great extent, be able to learn off policy. And when we do this, the algorithm, in this case, MetaMimic, is able to supersede the demonstrate. Other algorithms that use demonstrations also tend to supersede the demonstrate. Reinforcement learning algorithms, even very powerful distributed, recursive, and so on, recurrent and distributional are failed to do as well. Now this, by mimicking, in the case of the robot was mimicking its own behavior, so its own past behavior. So someone teleoperated it, and now we want to teach the robot to autonomously do what it was capable of doing via teleoperation. But sometimes the robot, you can't teleoperate a machine, and it might learn in third person. Like we would like what I showed in the beginning, which is, for example, for the robot to watch a video of someone doing something, and then the robot goes and does it. One step in this direction for me was this idea of, like, I was actually watching my nephew doing the thing here on the right. And I mentioned to my brother that, that he's wasting a lot of time with this. This is okay. And he's like, no, he actually learns a lot by doing this. He's always gets, A+ in math and so on. So that's why I realized that a lot of what we learn by going and watching YouTube. If you want to cook, if you want to do knitting, if you want to do, I don't know, karate or whatever. And so we decided that, being DeepMind, we do a lot of Atari. So I decided, okay, let's learn to play Atari by going to YouTube, watching the video, and then going and playing it. And so in this case, when you go and watch it again, you don't have actions, you don't observe rewards. All you observe is videos, and the videos are different because there's different versions. And of course, people insert ads and so on. So your method has to be robust to this. So there's a remap there. There's what we call the domain gap. And so what we need to do is to learn features, network features, that will be independent of, regardless of what video it is, what color configuration, whether there's ads or not. This network will get a set of features that will be independent of that. Once you have a set of features that's independent of that, then we can go back to the method that I just described, and we can do reinforcement learning, and we can learn to imitate the humans perfectly. And so, so we did precisely that, and the way we train this is we take, say, ages and frames, say frames at different distances, in this case, say, delta 3, and we treat this as a classifier task. We try to classify whether the distance between the frames is, say, 0 or 1 frame, or, or whether it falls in a different range. And that's enough to learn good ways of mapping images to a representation that is independent of which video quality or so on you're using. And this is done, of course, it's unsupervised. Of course, Atari has sound, so the nice thing is when we go to YouTube, you also get the sound, whereas in the simulator that we had, we didn't have sound before. So you can also check whether the sound occurs at the same time as the vision. And that's actually a very powerful clue. And here, for the features, we can compute the derivative with respect to the input, so we can see which features activate the most. And you can see that the neurons start activating for like objects and so on. What's interesting is when we do cross-model, they activate for objects like the key, because it produces a sound when you grab the key. So being multimodal, I think, is another lesson that we've learned. It really helps to be multimodal with our models. And then, of course, because we learned by RL, the guy on the right, the reinforcement learning agent, learns to actually be more efficient than the guy on the left. So it imitates, but it's actually able to, because it's maximizing reward, it's able to do better. I'm going to sort of go very quickly now. So the tasks that we've described so far, they, like the one of before the Atari one, it has sparse rewards. You only get rewards after many, many steps. So with standard reinforcement learning, it's impossible to train these models well. It learns from pixels or from sensors or from sound. But those environments are very deterministic, whereas the real world is in the real world, there's a lot of variability. In fact, if you wanted to make simulations more rich, you should have variability. If you're navigating in a maze or so on, you have partial observability. And these sources of uncertainty throw most methods off. In the real world, actually the real world, this world, it's even trickier because if you, just by changing where a robot hand starts by epsilon, and then following the same behavior, you can get either a behavior where this thing falls or a behavior where this doesn't fall. So epsilon changes in initial conditions can cause a dramatically different thing to happen in the environment of the robot. And this sort of thing happens all the time. And when this happens, someone needs to be next to the robot. So that sort of slows down iteration. One of the things we did was we constructed environments that had all these 4 properties. And very recently, we released an agent called R2D3. And that, again, is a distributed agent that uses a big experience replay. It uses a very deep neural network with a recurrent memory. And it's able to then go and solve tasks that look like this one, where an agent will say, find a bat, pick up a bat, hit a ball, pick up the ball, put it in the right sensor, and then it can get a reward, which is in this case collect apple. Building these massive distributed agents that make use of demonstrations allows us to solve some of these complex tasks. Other agents, like if you were to do imitation just by building a classifier or just pure reinforcement learning, you would get 0 reward for these tasks. So a task like this that involves some basic tool use is beyond any reinforcement learning without the use of demonstrations. Here's quickly an example of how it does. It hits the ball, it catches the ball in the air, it puts it in the sensor, gets the apple. Interestingly enough, in all its demonstrations, all the humans hit the ball, and then the ball falls on the ground, and then they pick it up. But this RL agent is so good, it actually catches the ball in the air. And there's a few more examples, which I'll skip. In StarCraft, again, it's a game that had another simulation which had a lot of complexity and for which we had a lot of data. And then it was also, we were also able to learn a policy. In that case, we actually used on-policy reinforcement learning, mainly because that's what was sort of feasible given the scale of the problem. And then you learn a behavior cloning policy, and then what you optimize is a mix of the reward plus being close to the behavior cloning policy. If you just optimize reward, it doesn't work. But if you optimize the combination of 2, then it works. So imitation is sort of crucial in that domain. Finally, I'd like to finish with this, which is how we do robotics. So in robotics, the idea is we teleoperate the robots these days. The data goes into a big storage space. If the robot also acts in the world by itself, that data also goes into this. Humans can be in the loop, and they can sort of say what the task is, in this case with a technique of reverse sketching that we will release soon this week, actually tomorrow. You can learn from this data policy by reinforcement learning. Importantly, if you use off-policy reinforcement learning with distributional RL or a technique called BCQ from Montreal, you're able to learn to teach a robot how to behave without executing the robot. So the idea is you pre-execute it, you learn a lot of behaviors. You teleoperate it, and then it learns to do this. And in this case, for example, it had never seen this object here that is trying to sabotage it. But regardless of that object being there, it always is able to solve the task, which is to put the green guy on the top of the red. So this kind of indicates the robustness of these methods. You can try to break them down. It will still do it. It just wants to solve the task. It's independent of these functions. A challenge here is how we evaluate these policies, because evaluate these policies is very time-consuming at this point in time. That's a topic that I don't have time to go into, but it's an interesting one. If we can teleoperate machines and then learn policies, the impact of this is going to be vast. The moment we learn, data has never been a thing in robotics. People build a thing, they might collect a small data set. No one's ever collected years of data for a robot. The closest it comes to that is autonomous driving, which a car for me is a robot. You operate it. You provide, the human takes vision and operates it by performing the motor commands you have to perform to drive it. So I think anything that has that kind of interface through collecting data will eventually be able to automate. What have we learned? All these things have been possible because we build very complex environments. Building environments takes years. Good environments takes years. Good, stable robotic environments also take years to build. It's very hard to get good manipulation devices and things that persist well and are robust. So this should never be ignored. You don't just go and build an environment and then your method is more important than the environment. No, actually, the environment matters a lot. And there's a lot of work that we still need to do. Good software for training RL agents is essential. Some of these RL agents that we have, they're the product of engineers working for several years, and we're talking about a team of 6, 7 engineers. We've heard about the issue of replicability in RL. The only way to solve that is to have good engineering. They're very complex pieces of software. It's important to reduce sample complexity, because obviously like robotics and so on is not going to work. We also can't be running processes that use as much electricity as this city for a week. So sample complexity, energy is one of the things we need to minimize, so we've learned that. The networks are very powerful. Networks essentially can implement algorithms. If you can get the skeleton right, you don't need to think about the mathematical details. Let the network learn the mathematical details. And of course, there's this connection about imitation and meta-learning, which I've already pointed out, between you thinking of people as tasks. Challenges ahead. Everything in the previous slide continues being a challenge. Imagination has helped. We haven't really explored this, and I think we should explore this more. Long-term imitation, like how do you cook? One way is you copy the recipe. So you go to the symbolic stratum, and then the next week you just from the recipe you generate again with a new oven and so on. You generate the cake that was baked by your friend the week before. But of course, we are so far from that kind of generalization at this point in time. Another challenge that would be useful to solve for imitation is when you know who you are and which are the other agents. And ultimately to know what you know and to know what others know, that kind of thing. That I think is an essential open problem. It's a hierarchical problem. It seems to be very obvious. It's just a model of a model, but no one has figured out how to train that. And of course, as I mentioned, abstraction remains elusive. We heard about core knowledge and maybe language that sort of through its production can help there. People have put in ideas of imitation and memes, which is actually a way of arriving at some forms of human abstraction. That would require selective attention, something that we have not touched upon. And of course, we're all very far from models that are capable of falsifying their own theories and so on. That's all I have to say. All this work is done by the folks here, as well as that photo is actually from our retreat last year. Farial and I just came back from our retreat this year, so I need to update this picture with a few more people. But they're the ones that did all the work that I've presented to you. Thank you very much.
All right, there's time for some questions, and if the speaker can just start switching while we go. Let's see.
I'm going to...
Yeah, fair, feel free.
So thank you very much. We've seen those amazing advances, and I would be curious about your opinion on what aspects we could focus on in neuroscience to investigate how learning is represented in biological systems, and maybe also on which abstractional layer we should focus doing that.
So it's hard to me to say like what you should get out of this, because but the hope I guess I had in mind was if you happen to be studying, say, imitation in a particular kind of animal, or so to kind of show something about what that animal intelligence is capable of, this should provide you some guidance of what sort of you can feasibly train in practice with reinforcement learning with a neural network. So it should give you with that guidance. The other thing I think it would be nice, what I'm saying I understand very little of, is this process of, say, selective attention, just to give an example. So if this community decided to go and do research on selective attention and be able to put examples out there, maybe tasks, maybe conclusions of, it's really out of my field, so, but if you reared cats that are capable of selective attention, that would be kind of cool. It's probably unlikely. But if you focus on solving these types of problems, or so much so, but study how selective attention, say, works with humans, that would be useful to me. Me and other people working in this area, because we could do more research along those lines. That's more or less.
I think we have time only for one more quick question, and while we switch, yeah, go ahead.
So I have a question over here. It actually builds off that previous question, I think. Maybe I'm over here. How you doing? So I was wondering if, given those embeddings that you're generating for each person as a task, or each instance as a task, if there's an opportunity there to explore the structure or the dynamics or just the dimensionality of the task not being the person, but the overarching task, and whether that can inform what the biological analog might be, like the structure as it's implemented in a... was my question clear?
It's an interesting question. So I don't know how you would... I mean, the embeddings would be some sort of, as Jeff Hinton says, some sort of thought vector, a subset of activations in, say, your neural circuit. How does that embed? I showed 2 ways in which you can get those embeddings. One is by sort of have a neural network that predicts that embedding, and one is by getting the embedding through an adaptive process. In this case, stochastic gradient descent. That embedding could also be produced by feeding language, and then you get an embedding. So if you have a vector that represents a sentence, if you believe in vector models for language, then that would be another way to get it. So you specify your task with language. When I walked into this room, I knew what to do. So if my task was to give a talk, then it's just based on my history and my memory, my internal state, and the observations I have, I can predict that embedding as well. So in this case, I see it more as a continuous process, evolving in time, taking observations. So from that process, you predict that embedding, and that embedding sort of determines your behavior. I would not know where to look for such an embedding in the brain with neural correlates and so on. I don't know if that's the right way to approach it. My main intention there was to kind of show that just with a vector, you can do a lot of things. It's a very powerful concept. It's a way of summarizing language, a way of summarizing a behavior, summarizing programs, summarizing different traits of different people. It's really like latent variables in the old Bayesian models. And I also wanted to show that that way of training, when you focus on many tasks with few data toward getting embeddings that then you can adapt quickly, is actually, it works. It works in practice. We can solve real problems that are important, like restoring people's voices. We can copy anyone's, we can do far more than that, in fact. It's a very powerful paradigm. You can do it with MAML as well. You can do it with all the meta-learning techniques, pretty much. And the point being that meta-learning is working. It works really well in practice. And so people in neuroscience have started studying it, like Matt Botnick. And I highly recommend thinking of it in those terms. It's like how, through successive trials, we actually learn knowledge that can be reused efficiently. For me, it resolves a lot of this innate versus adaptive thing. Because you could think of, like, through the process of evolution, we've learned that core model, the core knowledge, and then what's left to be adapted quickly. That's kind of like what I'm putting in that embedding. But it could be something different than an embedding. It could be different modules, like what Ferial did recently. And of course, that doesn't just work at evolutionary scales, but as psychologists have shown, that happens at multiple scales. That happens even in seconds and so on. So I guess the message is meta-learning works. It's very powerful. Keep working on it, because I've drawn most of my inspiration from meta-learning from the psychology literature. So I thank you for that.
All right, let's thank Nando. I know there are more questions, so we have to move on.